All right, let's dive right in. Today, we're going to be detectives, cracking open a really old case from the history books of computing. We're going way back to look at one of the very first attempts to solve a huge problem. How in the world do you share a computer's limited memory? So yeah, let's head back in time and see how the pioneers of computing first tried to tackle this challenge.
Think about it. Right now, you're probably running a bunch of different things on your machine. That magic is called multi-programming. But for any of that to work, the operating system has to solve a giant puzzle first. Where does it put everything?
You see, at the heart of it all is the fact that your computer's memory, its RAM, is a finite workspace. Every single app you run needs its own slice of that pie. And it's the operating system's job to be the ultimate manager, deciding who gets what.
Let's picture your RAM like a big, empty warehouse floor. The very first thing to move in is the operating system. You can think of it as the warehouse manager. It walls off its own little office space, and all the remaining floor space is what's left for every other program or process that needs to be loaded up. So, faced with this empty warehouse, what was the first big plan? Well, early OS designers went with a really straightforward idea called fixed partitioning. The thinking was, hey, let's just bring some order to this chaos by planning out all the spaces ahead of time.
Now, the key thing to get here is that this division happens before any of your programs even ask for space. The system carves up the entire available memory into these fixed slots or partitions. And that layout? It's set in stone from the get-go.
And this approach really came in two main flavors. You can make every single partition the exact same size. Super simple, right? But also really rigid. Or you could try to be a bit more flexible and create partitions of different sizes, hoping to fit different kinds of programs. But, as we're about to find out, both of these versions had the same, well, fatal flaws. And this is where our detective story really kicks into gear, because this neat, tidy solution had a massive, leaky hole in it. A problem of wasted space so common that it got its own special name.
It's called internal fragmentation. And that word, internal, is the key. It means the waste is happening inside a memory block that's already been assigned to a program. So, how does that even happen?
Let's walk through it. Imagine there's a 4 megabyte partition just sitting there, ready to go. A new program comes along that only needs 2 megabytes. The OS says, perfect, here you can have this 4 megabyte slot, but the program only uses half of it. What about the other 2 megabytes? Well, it's left over, trapped inside that partition. And because the whole partition is now assigned to that one process, that extra space can't be used by anything else. It's just wasted.
Let that sink in. In this one really simple example, a full 50% of the memory that was handed out is completely useless. An entire half of that space, just gone. And believe me, that's just the start of the problems.
Yeah, beyond just wasting space, the fixed part of the system created some really harsh limits on what a computer could even do. What started out looking like an elegant design was quickly turning into a straitjacket.
First, you've got a strict limit on how big a program can be. If your biggest partition is 16 megs, but you've got a program that needs 32, well, too bad. It just can't run. End of story. Second, it puts a hard cap on your multitasking. If you decided to make 4 partitions, you can only run 4 programs at once. That's it. Want to open a 5th app? Sorry, no room at the inn.
But all of this leads us to the most baffling problem of all. A complete paradox where the system could have plenty of free memory available, but be totally unable to use it. This is the flaw that truly, finally doomed fixed partitioning.
Okay, so here's a snapshot of our memory. As you can see, every partition is being used. In that first one, a 2 megabyte process is wasting 2 megs. In the next two, we have some 7 megabyte processes, each wasting 1 meg. And in that big one at the bottom, a 14 meg process is wasting another 2 megs. See all that leftover space? Now, if you add up all those little bits of wasted space, you get a grand total of 6 megabytes of free memory. So here's the critical question. Can we run a brand new process that needs just 5 megabytes? We have 6 megs free, so the answer should be yes, right?
The answer is a hard no. Even with more than enough total space, the new program gets rejected. But why?
This is because of the second type of fragmentation, and this one's called external fragmentation. This is what happens when you have enough free memory, but it's all broken up into little disconnected chunks scattered all over the place.
The problem is that our 6 megabytes of free space isn't in one useful block. It's splintered across 4 different partitions. And since programs need one single continuous block of memory to run, none of those small leftover chunks are big enough to hold our 5 megabyte process. The space is there, but it's totally unusable.
So, when we step back and look at all the evidence, the verdict on fixed partitioning becomes crystal clear. You know, it was an understandable first try, but it was ultimately a dead end.
Let's just recap the case against it. You've got two different kinds of wasted memory, internal and external fragmentation. You have a hard cap on how big your programs can be, and you have an artificial limit on how many programs you can even run at the same time. So what was its one redeeming quality? It was easy. The logic was simple to implement, but that simplicity came at a huge cost. It was incredibly inefficient and completely inflexible.
This method definitely had its moment, way back in the 1960s, on those early mainframe computers, but you have to see it as a necessary stepping stone. The failures of this system are exactly what pushed engineers to invent the much smarter, much more dynamic ways of managing memory that all of our modern devices rely on today.
At the end of the day, fixed partitioning taught us all a really valuable lesson. The simplest solution isn't always the best one. Its initial appeal made sense, but that cascade of problems, from wasted space to programs that couldn't even run, was just too high a price to pay.
Which, of course, leaves us with a really juicy question for next time. If this super simple approach failed so badly, what kind of clever tricks and complex systems came next to fix this mess? Well, that is a story for another